Everyone, welcome to this explainer. Let's just jump right in, because today we are basically playing scientific detectives. We're going after one of the most notorious rule breakers in the entire world of chemistry. You know, if you've ever analyzed a nuclear magnetic resonance, or NMR, spectrum of an organic molecule, you're probably used to a nice, orderly, predictable set of data. But the second nitrogen enters the chat, total chaos. So today, we're opening up the case of the misbehaving nitrogen and exploring a really fascinating chemical detective story full of wandering protons, disappearing peaks, and some pretty strange quantum mysteries.
So here is our central mystery for today. Why do protons attached to nitrogen absolutely refuse to follow the standard rules of NMR spectroscopy? Normally, an NMR spectrum gives us this beautifully crisp, organized picture of a molecule's hydrogen atoms, right? They're neatly sorted out by their magnetic environments. But when those hydrogens are attached to nitrogen, like what we see in amines and amides, their peaks often turn into these blurry, unpredictable smears. They completely ignore the rules. To figure out why, we need to take a close look at the evidence. And propylamine is the perfect crime scene to start with. Notice the sharp, well-defined peaks for the carbon-bound hydrogens on the right-hand side. Totally normal. But now, check out the absorption around 1.8 parts per million. Those are the hydrogens attached directly to the nitrogen. Instead of sharp, clear peaks, we just get this weak, broad, blurry lump. And what's even more suspicious? There is a complete lack of coupling between the hydrogens on the nitrogen and the hydrogens on the adjacent carbon atom. It's like they don't even know the other guys are there.
Now, to really appreciate how weird this behavior is, let's quickly review what should be happening. We all know the standard rules of NMR dictate that we should see spin-spin splitting. This is the whole empirical n+1 rule, right? Basically, a proton acts like a tiny magnet and it senses the magnetic spin states of the equivalent protons on neighboring atoms. If a proton has n neighbors, its peak splits into n+1 components. Simple enough. But our nitrogen-bound protons in propylamine are literally ignoring their neighbors entirely. So who or what is responsible for this decoupled blurry mess? Well, we have three prime suspects.
Let's bring in suspect number 1, which is chemical exchange, or as I like to call it, the fast swap. In simple amines, the protons attached to the nitrogen aren't exactly loyal to their parent molecule. Because those protons are slightly acidic and the nitrogen is basic, they are constantly hopping off one molecule and onto another through intermolecular proton exchange.
You can kind of think of this process like a microscopic, high-speed game of musical chairs. In a free amine, this proton exchange happens incredibly fast. The proton swap places way faster than the NMR spectrometer can actually snap a picture of them. Since the protons are frantically jumping around, their spin-spin interactions with adjacent carbon protons get completely decoupled. The NMR camera just captures a motion blur, which leaves us with a single, unsplit, broadened peak.
But we can actually interrogate this suspect and stop the madness. By dropping the pH of our solution below 1, we create a strongly acidic environment. This massive flood of excess protons forces the amine into a protonated state, a quaternary ammonium cation, and that effectively ends the game of musical chairs. It slows the chemical exchange down so much that the protons are forced to stay put, and once they sit still, the NMR camera finally gets a clear shot, and that hidden spin-spin coupling suddenly reappears. So suspect number 1 is officially caught.
That brings us to suspect number 2, the quadruple broadening mystery.
Now, the fast swap doesn't explain everything. It falls short especially when we look at amides, which just don't undergo that rapid swapping quite as easily. So to understand our second suspect, we have to look deep into the nucleus of the nitrogen atom itself. Elements that have a nuclear spin quantum number, or I, greater than 1/2, have what's known as a quadruple moment. Unlike protons, which have this nice simple spherical charge, nitrogen's nucleus has an ellipsoidal egg-shaped charge distribution. Because it's unsymmetrical, the nucleus acts kind of like an indecisive wobbly spinning top. It's incredibly sensitive to the electric and magnetic environments created by the valence electrons around it.
This wobbly nature means nitrogen can exist in 3 very distinct quantum states, depending on the molecule. If the nitrogen sits in a highly symmetrical environment, like an ammonium salt, it has a small quadrupole. Here, it behaves normally, and the proton-nitrogen coupling is crystal clear. On the total opposite end, with a large quadrupole, the nitrogen nucleus rapidly flips between its spin states. It's moving so unbelievably fast that the attached protons just see an averaged 0 spin, giving us a neat, sharp singlet. But the real headache? That happens right in the middle, with a moderate quadrupole.
The spectrum of Perol is pretty much the textbook example of this chaotic middle ground. Notice that massive, stretched-out bump spanning all the way from 7.5 to 8.5 parts per million. That is an extreme case of the moderate quadrupole effect in action. The nitrogen spin transitions are happening at an intermediate rate. It's not fast enough to average out to zero, but it's definitely not slow enough to resolve into neat, clean splits. The attached proton is just thoroughly confused about what magnetic environment it's actually in, and that confusion causes this extreme peak broadening.
And finally, suspect number 3, the case of restricted rotation.
All right, so we've tracked down the fast swap and the wobbly nucleus, but there's one final culprit we need to talk about, and this one specifically targets amides. While amines can spin around freely, amides are built totally differently. Let's compare them. In a standard amine, the carbon-nitrogen bond allows for free, rapid rotation. Think of it like a spinning propeller. But in an amide, we get a resonance interaction. The unshared electron pair on the nitrogen shares electrons with the adjacent carbonyl oxygen. This resonance gives the carbon-nitrogen bond a partial double bond character, and that forces the entire molecule into a rigid, flat, planar geometry. Basically, the propeller gets locked in place.
So what's the actual consequence of locking that geometry down? Well, because the rotation is restricted, it means that two supposedly identical groups attached to that nitrogen, say two methyl groups, cannot freely swap positions anymore. One group is permanently stuck on the same side as the carbonyl oxygen, and the other is stuck on the opposite side. Because they're locked into these different physical spaces, the NMR spectrometer views them as being in magnetically completely different environments, which means they're going to show up as two separate peaks instead of one.
Now, we can absolutely prove this lock exists by forcefully breaking it. NN-dimethylformamide gives us the perfect smoking gun evidence here. These spectra were taken at varying temperatures. We're essentially going to use intense heat as a truth serum to speed up the molecular rotation and force those peaks to reveal what's really going on.
Let's walk through this temperature timeline. Down at a cool 25 degrees Celsius, the molecule is locked tight. The NMR sees two magnetically distinct methyl groups, which gives us two sharp, separate peaks. Now let's turn up the heat. At 100 degrees, the rotation starts fighting against the lock, and the peaks begin to widen and broaden. By 120 degrees, the groups are spinning fast enough that the peaks merge into one big, broad lump. And finally, at 150 degrees Celsius, the thermal energy is so intense that the bond is just spinning furiously. The NMR spectrometer can only see one rapidly averaging environment, leaving us with a single, sharp, unified peak. Heat completely solves the case.
So, case closed, taming the nitrogen spectrum. Okay, let's take a quick breath. We have successfully investigated all these strange anomalies of nitrogen in organic molecules and brought some serious order to the chaos. The absolute main takeaway from this explainer is this. Whenever you see a broad, messy, or totally weird peak for a nitrogen-bound proton, you are looking at the handiwork of one of three culprits. First, quadrupole broadening, that wobbly nucleus blurring the magnetic environment. Second, intermediate proton exchange, a rapid game of chemical musical chairs messing with the NMR camera. And third, restricted rotation, the locked planar resonance in amides forcing identical groups into different magnetic zones.
We've seen how simple little tweaks like adding heat or dropping the pH can unmask these culprits in small, simple molecules. But I want to leave you with a pretty wild thought to ponder. If these bizarre quantum dynamics, the exchanging, the wobbling, the geometric locking, are all happening in basic amides and amides, just imagine how insanely complex these rules become when you apply them to massive biological chains of amides. I mean, think about the proteins folding and unfolding inside your own body right at this very moment. It's a huge puzzle, but that is a mystery for another day. Thanks for joining me on this explainer, and keep questioning the evidence.